Greetings to everyone. This is the second presentation for design and analysis of algorithms. Let's look at the longest common substring problem. It states that given two strings, the task is to find the longest substring that is common between the two strings. And by substring, we mean an array of characters that is contiguous. So the input can be two strings x and y, and the output is the longest possible substring which is common to both x and y. The question we ask here is, can we compute the longest common substring in O of n, which is linear time? The answer is yes, it is possible. We can compute the longest common substring in linear time using something called as suffix tree, or rather generalized suffix trees. So first of all, let's look at the ON squared solution, which is a quadratic solution which can be achieved using dynamic programming. Let's go through an example. As we can see, there are two strings, one we have kept vertically and another horizontally, and we initialize a matrix of the size as shown with zeros, and after filling the 0th row and 0th column with zeros, we start traversing the matrix row wise, and basically the rule is, if the ith character of the vertical string is equal to the jth character of the horizontal string, then the cell of the matrix ij is equal to the cell which is diagonally behind the current cell, which is I minus 1 j minus 1, and the value of that, and just add 1 to it. So basically it is one more than the cell which is diagonally behind it if the ith and jth characters of the respective strings are equal, otherwise it's 0. So if we look at an example, as you can see here, both of these characters are y, and thus the value of this cell is the value of the cell which is diagonally behind, which is 0 plus 1, which is equal to 1. If you look at the cell next to it, the characters are not equal, and thus the value of it is 0. So basically we fill the entire matrix like that, and ultimately the maximum number in the entire matrix gives us the length of the longest common substring, which in this case is 3. We can also trace the diagonal backwards to get the actual longest common substring. So we can just go backwards until we reach 0, and we can just get the longest common substring, which is y, z, and w. So now let's try to get this same substring in linear time instead of quadratic time, so that we can say that we can do it more efficiently, which we definitely can. So for that we need to understand the concept of suffix trees. So suffix trees are data structures to store all possible suffixes of a string. Let's take an example. For our previous horizontal string, x, y, z, w, x, v, dollar. Basically a dollar is a unique character which is assigned to signify the end of a string, and that string will have possible suffixes like dollar, v dollar, x v dollar, and so on. So basically the string including the dollar sign has length 7, and thus it has 7 possible suffixes. So at the right we can see the example of a suffix tree. So the suffix tree is as I said earlier, a data structure which captures all the possible suffixes. So if you look at here, if we start with the root, this is the root, and if we start here, we can get the first one, which is the dollar, then the second one, which is v dollar, then the next one, which is x v dollar, as we follow the different branches. Ultimately we get to the last one, which is x y z W, X, V dollar, etc. So this is a suffix tree. Uh, so okay, mm, how does this help us to find the longest common substring? For that, we need to understand another concept, which is generalized suffix tree. So a generalized suffix tree contains suffixes of more than one string. A normal suffix tree is just for a single string, whereas a generalized suffix tree is for multiple strings. So once we have a generalized suffix tree of two strings, finding the longest common substring is extremely easy. So again, if we go back to our original example, so we have these two strings xy zw xv dollar and ay zwv hash. Again, dollar and hash are unique and characters, as discussed earlier. We see that the branch of yzw, which we can see here, is the longest branch with children from both strings. Okay, so as we can see, this is the root node, and then there are multiple leaf nodes, and then there are multiple internal nodes as well. So if we look at each internal node, uh, there are uh, there are 4 internal nodes here which have children which come from both the strings, and among them the longest branch is y, z and w. So basically y, z and w is the longest common substring because it is included in both the strings. As we can see, it has children from both the strings, and therefore it is the longest common substring. So once we get the generalized suffix tree, we can see it is very easy to compute the longest common substring. As the number of nodes in the generalized suffix tree is linear, we only have to check all the branches only once given a generalized suffix tree, and thus longest common substring can be found in linear time. Therefore, this implies that if we construct a suffix tree or a generalized suffix tree in linear time, then computing the longest common substring is possible in linear time. So the problem here is, can we construct a suffix tree in linear time? It turns out we can. So a suffix tree can be constructed in linear time using Ukkonen's algorithm. But before we go to the algorithm, we need to understand some terminology. We can divide this into sections. So first we'll go through extension rules, then some modifications to those rules, then the concept of suffix link, and then the concept of active entities. This might seem a bit overwhelming right now, but as we go through each and every step, each and every concept, and then once we look at a few examples, it will become very clear. So first, let's have a look at the extension rules. Rule number 1 says, if the path from the root ends at a leaf edge, then the next character is just added to the end of the label on that leaf edge. Rule number 2 states that if the path from the root labeled like that ends in a non-leaf edge, and the next character is not the character which we currently have at hand, then a new internal node will have to be created in between. So it will break off at that point. Rule number 3 states that if a path from the root is labeled as such and it ends at a non-leaf edge, but the next character which is at hand is already present as the next character in that particular branch, we do nothing. I understand that this can be very confusing. to read just like that or to explain just like that. So we'll just have a look at an example to see how these extension rules work. So let's have a look at a simple example. I have my previous string which we used earlier, x, y, z, w, x, v dollar sign, and we'll just use the three extension rules and try to create a suffix tree. So yeah, let's start from the first character. So do we have a branch which starts with x and ends with x? No, we don't have it. So we'll start at the root. This is the root, and we'll make a new branch and assign x to it. Okay, so let's move on to the next character. So now we are at this character. So do we have something which starts with x and ends with y? No, we don't, but we have a branch with x. So a rule 1 extension will apply, and we'll add y here. Previously a rule 2 extension was applied because there was no branch, so we added a branch. So now do we have something which starts with y and ends with y? No, we don't. So a rule 2 extension applies, and we create a new branch which is y. Okay, so this phase is over. Let's move on to the next phase. So okay, so we come at z. Do we have something which starts with x? Yes, we do. But do we have something that ends at z? So do we have x, y, z? So we have something, we have x, y, but we don't have z. So a rule 1 extension will apply, and we'll insert z right here. Same thing, if we start with y and end at x, we do have something starting with y, but we don't have it ending at z. So rule 1 extension again, and so something with only z we don't have, so we'll create a new branch with rule 2 extension, and it will name it z. Okay, end of this phase. We'll move on to the next phase. So as we move on to the next phase, we'll see that we don't have something. We have x, y, z, but we don't have w there. So rule 1 extension, and we'll add w. Similarly for y, z, w, we don't have it, so we'll add it here, rule 1, and z, w according to rule 1. Again, we don't have something with only w, so we'll create a new branch and name it w. Okay, so let's proceed to the next character. So here we are looking at x. So do we have something which starts with x, goes to y, z, w, and then again x? No, we don't. So by rule 1, we add it right here. Then again, do we have something that starts with y? Yes, we do, but we do not have it ending with x. So we'll put x right here according to rule 1. Similarly for here and here. Now, do we have something that starts with x and ends with x only? Right here. So we have something which starts with x and we can end it right here. We have nothing here. So a rule 3 extension applies, which means do nothing. So we can move on to the next character. We'll go to v, and so as we can see, uh, do we have something which starts with x, y, z, w, x, but without v? Yes, we do. So we add it right here. We'll just extend this branch a bit. Same goes for here. We'll just extend this branch as well. Then again it's true for this branch also, and again this is true for this branch also. Next, we have come to something starting with x and ending at v. So we have something starting with x, but that ends right there, and the next character is not v. So a rule 2 extension applies, and here we'll have to make an internal node and branch it off and get this new character v. Do we have something which starts with v and ends with v? No, we don't. So we create a new branch and name it v. This ends the current phase and we move on to the next one. So we go to the last character, which is dollar, and again we scan something starting with X, Y, Z, W, X, Y, V. Yes, but do we have dollar sign at the end of it? No. So rule 1 applies here. I'm sorry, let me just draw it again neatly. So again, I'm sorry again. I don't. I'm apologize for this. Uh, so yeah. Mm, Again, we look at the same thing starting with Y ending with dollar sign. So rule 1 extension applies, and we have to add a dollar sign here, a dollar sign here, and dollar sign here, a dollar sign here, and a dollar sign here as well. So now, do we have something which starts with dollar and ends with dollar? No, we don't. So in this case, we branch a new item and we name it dollar sign. And this concludes the construction of a suffix tree from the string. So this is our final suffix tree. As we can see, we have all the possible suffixes: a dollar, v dollar, w. I'm sorry. So, let's start again. So we have dollar, v dollar, xv dollar, wxv dollar, zwxv dollar, yzwxv dollar, and xyzwxv dollar. So we have all the 7 suffixes, and this is the complete suffix tree. How much time did it take? This took an n-cubed amount of time, because we are following basically 2 loops. So like the first loop is traversing through each character, and the second loop, the inner loop, is traversing through all the characters which have been till now. And during the uh, consideration of 2 of such characters, like every pair, we have to go through each and every character before it to check if we have something, uh, and like which rule extension we have to apply. So in totality, this is an n-cubed algorithm, but it can be applied in a very efficient manner, and we can reduce its complexity greatly. So there are some modifications we need to do, and there are some new concepts that need to be introduced. So we will look at those next. So now we have had a look at the example, but as you saw that even after using the 3 rules, we get suffix tree in a cubic time, which is worse than the dynamic programming solution. So we need to do some modifications to those rules so that we can reach the final form of Ukkonen's algorithm, which will give us an efficient solution. So the first modification which we make is that we use a global end, which is we maintain a global end, an end variable. So whenever a new character is introduced, it gets automatically added to all the leaf edges. So whenever there is a rule 1 extension, we won't need to have to do anything. It will just automatically get updated. So every variable, whenever rule 1 extension is applied, can be added in constant time. So that saves us a lot of time. And the second modification is that if a rule 3 extension is observed, we'll stop the current pass right then and there and move on to the next character. Because like when a rule 3 extension is applied, we generally do nothing, and after that checking all the remaining characters in the pass becomes redundant, and thus we can just stop it right there and start the next pass. These are the 2 modifications. Of course, there are some syntactic and convenience modifications as well, like storing the string in every branch is not recommended. Rather, we just store the indexes like the range of indexes uh, of the characters which are there in the particular branch and stuff. But well, that is more relevant while actually coding up the algorithm. mm, so yeah, let's proceed further. So these are the two major modifications which we apply uh, to the extension rules for Ukkonen's algorithm. Now we need to understand a few more concepts before we dive into the actual algorithm. So first one among them is called a suffix link. So by definition, this for every internal node with a path t alpha, where t is the starting character and alpha can be 0 or more characters, there is another internal node which is with alpha, which is a suffix link of this node. So for example, as we can see on the right, if we start at the root and if we go here, so this branch has a path abk, and this branch again, as we start from the root, has the path bk. So in accordance, the suffix link of this particular node is this particular node. So why do we bother about these suffix links? It's a very important concept which aids in decreasing the complexity of this algorithm. And how does it do so? It enables us to hop between the nodes within the same pass, and thus we don't have to go back to the root to traverse the entire thing again, and that reduces the complexity to a great deal. Now, every internal node will have a suffix link to either another internal node or to the root, and this is a theorem which states the same. Now, how are these suffix links determined? So whenever an internal node is created, if another internal node is created in the same pass, the second node is the suffix link of the first node. Otherwise, the root is the suffix link of the first node. Again, this might sound a bit confusing right now, but it will become clear as we go ahead. Next, we'll look at the definition of active entities. So the active node is the node closest to the current location on a particular branch of the suffix tree. The active edge is the index of the actual character we are on, or the current location, and the active length is the indicator of the starting location of the next phase. So if the active length is 0, the next phase will start from the active node, and if it's a non-zero number, it will start from that many number of steps away from the active node. Basically, it's the distance from the active node from where the next phase will start. So for example, let's say we are here at j at some point in the algorithm. So right now this is the active node. The active edge is the index of j in the actual string, and active length would be 1 and 2, as it is 2 steps away from the active node. So this is a short description of what active entities are. There are 3 active entities, and there are some rules associated with these active entities. So let's look at those. So now there are a few rules concerning the active entities. So the first rule is in relation to the rule 3 extension. So we know that if a rule 3 extension, what is a rule 3 extension? That if we reach the end of a path and the next character is already present, we do nothing. So if a rule 3 extension happens, if we are moving along the same edge, just increment the active length by 1, and if we are jumping a node, we have to adjust all the active entities accordingly. We'll see how in a short while. The second rule is in accordance with rule 2. Uh, so there are two cases to that. So for the first case, if a rule 2 extension happens, that is, if we reach a point and the next character in the string is not there, so we have to make a new path. So if the rule 2 extension happens, and if the active node is root and the active length is not 0, we go to the active node, uh, whatever is the active node, which is the root in this case, and we increment the active edge by 1 and decrement the active length by 1. In the second case, if a rule 2 extension happens and if the active node is not root, we follow the suffix link. Again, right now you might feel that this is quite overwhelming and there are a lot of rules and a lot of concepts and a lot of things to keep in mind, but everything will become very clear as we go through an example. But before we head on to the example, another important thing to note is we need to name all the leaves once we have a complete suffix tree with us. So what do we do for naming the leaves? After we have completed designing every branch of every suffix, every branch of the entire suffix tree, what we do for naming the leaves is that we follow a DFS traversal, depth first search traversal, and we count the characters along the edges, or in the actual algorithm's case, the difference between the indices, which we store alternatively. But yeah, just for simplicity, let's say like while moving through the edges, we count the characters on the edges, and the leaf is assigned the value, the length of the string, the total length of the string, minus the number of characters encountered on that particular edge. And we name all the leaves as such using that principle. Again, so this just added an extra step, and still it hasn't simplified. So let's simplify our entire understanding of Ukkonen's algorithm with an example.
All right, so let's look at an example for the construction of a suffix tree using Ukkonen's algorithm and all the techniques we have learned till now. So I chose a string def deg dollar sign. This is because this particular string will let me showcase all the rules with their modifications and all the concepts like suffix link and active entities very effectively. So let's start. Before we start, I have initialized a few variables right here. So the rem variable will show us how many uh, uh, leaf nodes are supposed to be created in a particular pass. The active node, as we know, which is the root right now, because it's the only node in the diagram right now. The active edge and the active length. So we'll initialize them to -1 and length 0 respectively. And the end signifies the global end, which is quite helpful, as we'll see very shortly. So we'll initialize it to -1. So let's start. We'll start with the 0th character, which is D. So pass 0. So at the start of a phase or a pass, we increment the variable rem, and we modify the end such that it is matching the uh, index of the current character. So we don't see a path to D from the root. So root 2 extension applies and we create a new path D. I'm purposely making it a long one as it will be clear very shortly the reason. And as we have created a new leaf, we decrement rem to 0. As rem becomes 0, the pass ends and we move on to the next pass. So next pass means that we go to the next character, which is E. We increment rem and we also modify the end variable, and it becomes 1. Now, as the end has changed, a rule 1 extension applies, and all the paths uh, get added the new letter, which is E, as there is only one path right now, so we'll add it to that. This is the use of the global end. So whenever a global end is modified, all the paths directly have their end modified in constant time, which makes the algorithm very efficient. So now, as the active length is 0 and rem is 1, we still need to make a path to E by rule 2 extension from the root. So we'll do just that, and we'll make a path E. Now we'll decrement rem becomes 0, and we move on to the next pass. Next pass starts here. So the character in question is F. We increment our rem by 1. We modify our end by 1 as well, and we apply the rule 1 extension and add all paths with the character F, the current character. Now, as active length is 0 and rem is 1, we again have to make a new path from root to F according to rule 2. So we'll do just that, and we'll write F here. We'll decrement rem. Rem goes down to 0, which means the pass ends, and we move on to the next pass. Next pass, pass number 3. The letter in question is D. So we increment rem as business, and we modify end as well. So rem becomes 1 and end becomes 3. As end becomes 3, rule 1 extension applies, and we can add the character to the end of all of the paths. Now we look that does the path starting with D exist? Yes, it does. This time it does exist. So the rules say that we assign the active edge as the path in the starting we define the active edge as the starting node in the direction of that particular edge with the current character. So that will be 0, starting index of this particular edge. And our active length will be incremented as this is a rule 3 extension. How is it a rule 3 extension? Because a path starting with D already exists, and there are characters in the head in front of that. So a rule 3 extension is applied, thus active length is incremented to 1. And of course, as a rule 3 extension modification says, we just stop the pass if a rule 3 extension is applied. So that means that this pass is ended, and we move on to the next pass. So next pass, pass number 4. So the letter in question is E, and we increment the rem and modify the end as per usual business. This means that as end is modified, rule 1 extension is applied, all the paths get added the letter E, and we add it as follows. Now we start from the active point. So where is the active point? So active point is move in the direction of the active edge from the active node in active length number of steps. So we move 1 step in direction of 0, which is D, from root. So this is our current point right now. the active point. So we check the next character. The next character on the path is E, which is same as the current character in question, which is also E. Thus, a rule 3 extension will apply, which means that we have to increment. We have to increment the active length, and thus also stop the pass. So we'll stop the current pass and we'll move on to the next pass. So now the character in question is G, pass number 5. We increment a rem, we increment, apologies for that. We increment rem, rem is incremented to 3, and end is also modified accordingly. And as end is modified, a rule 1 extension is bound to come, and all paths get modified accordingly. Now, next character on the path. So firstly, we determine the active point. So it's at a distance of 2 in the same direction. So from the root, so the current point is here. The next character on the path is F, but the correct character in question is G. So they are not equal. Thus, a rule 2 extension is applied, and we'll have to create a new path from that particular point. So we create a new path. So this demands the creation of an internal node and the creation of a new path, which we will name as G. Okay, let's make it a little more on the side, because the space will be required for some other needs. So okay, so we created a new path for G, which also means we created an internal node, and that means that we have to create a suffix link, which for the time being will point to the root. And as we have created a new internal node, let's name it, let's call it P, and just a circle just to differentiate it from the other letters. And we'll decrement rem to 2 as we generated a new leaf node. Now, as the active node is still the root and the active length is not 0, the rules say that decrement the active length by 1 and increment the active edge by 1. Now, let's move on to the current point, the active point. So what's the active point? The active point is from root, we go one step in the direction of character with index 1, which is E. So right now this, oh my god, I'm so sorry. Right now this is our current point, and let's check the next character on path, which is F. The next character in question, the current character in question is G. They are not the same. Therefore, again a rule 2 extension will apply, and we'll have to create a new node right here and a new path right here with G. Now, which also means that we have to create a new suffix link, and the suffix link right now currently will point towards the root. As we know that if a new internal node is created, the previous suffix link has to be modified such that it points to the newly created internal node. So the previous suffix link will need to be modified, and we will point it to the very new node which has been created, which we can name as Q right here. And yeah, let's point it here. It's becoming a little messy, so let's just write it a bit properly. So this will be E, this is the suffix link pointer, and this is the suffix link pointer from here. All right. So let's move on. As this is a rule 2 extension, first of all, we'll decrement rem by 1. And as it is a rule 2 extension and the active node is still root and the active length is not 0, we'll modify the active length and the active edge such that the active length will become 0 now and active edge will become 2. Now, as active length is 0 and rem is still 1, we'll have to ask, do we have a path from root to the current character? We do not have, therefore rule 2 extension will apply and we'll have to make a new path to G. Alright, and of course we'll decrement rem, so rem becomes 0. Alright, let's go to the next pass as rem has become 0 and the letter in question is D. Again, as per the usual business, at the start of a pass we increment rem and we modify the end, and as end is modified, all of the paths get a new character at the end. So this is D, this will become D, this will become D, this will become D, this will become D, and this will also become D. Now let's go to the current path. So what will happen is what is the current path? So the current path, so we are at the root and the next character is definitely D. So next character on the path is the current character. So the active length will become 1. We just increment the active length and we modify the active edge such that it is the active edge as the definition goes. So the active edge will become 0 and the active length will become 1. As it is a rule 3 extension, we just stop the pass and move to the next one. So at the start of the next pass, the character in question is E and pass number 7 will begin. We can increment rem by 1, modify the end, so it will become 7. Rule 1 extension will apply. All the paths will get a new letter which is E. E here, E here, E here, and E here. Alright, so now we go to the current point. So the current point is 1 in distance of the active edge, in direction of the active edge. So this is the current point, and the next character is definitely the current character. So both are the same, which is E, and that means that rule 3 extension will apply. As rule 3 extension will apply, we just increment the active length. So it goes to 2. So active length goes to 2. And of course, as it is a rule 3 extension, we just stop the pass and move on to the next one. So we come to the penultimate character, pass number 8. So as per usual business, we increment rem, we also modify the end, and therefore as end is modified, all the paths get an additional character which is F. F here as well. Let's extend this, F here and F here. All right, so now we followed the rule 1 extension. Now let's go to the current path again, the current point, I'm sorry. So the current point is 2 steps in the direction of the active edge, which is 0. So so it's in direction of D, and the current point will be this one. So all right, so is the next character the same as the current character? Next character is F on the path and current character is also F. So yes, they are the same. So what will happen is we'll have to jump the node, and go here, and whenever a node is jumped, the active node changes. So the active node becomes P, the active edge becomes the index of the path, the index of the edge, starting index of the edge, which is the index of f, which is 2, and the active length will become 1. Also, this is a rule 3 extension which was applied right now. So the pass will stop then and there, and we move on to the next pass. So pass number 9, the character in question is the dollar sign. So as per usual business, we modify rem, increment rem, modify the end, so it becomes 9. Now, of course, as per usual business, the new character gets added to all the paths. So we add it here, we add it here, we add it here, and we add it here. All right. So okay, again we go to the current path. So we go to the current point, the active point. So the active point is 1 in the direction of the active edge, so 1 in direction of f from point P, which is the active node. So that is the current point, and the next character in the path is D, but the next character required is the dollar sign, so it is not what the current character is, so that demands the creation of a new branch which will get its own character dollar sign by rule 2 extension. So of course, as every time whenever a new rule 2 extension is created, new internal node is created, we create a suffix link. So the suffix link will go from being the suffix node. The suffix link will go from this point. Let's call this point R. This will point to the root right now. So we just point it to the root for the time being. And as we know, this time, as the active node is not root, what we do is we follow the suffix link of the active node. So currently the active node is P, and following the suffix link of active node, we reach Q. So the active node becomes Q. As active node becomes Q, we also change the path. So the path is in direction of f, one point in direction of f. So let me erase this, and we'll go to the current path and the current point. So the current point right now is f. So the next character in path is D, and the next character in the string is not D, it's dollar sign. So we'll have to create a new node right here and give it its own character, the dollar sign. And as a new character is created, a suffix link is also created. Let's name this internal node as S, and the suffix link can point to the root for the time being. Also, the previous suffix link will have to be modified. So this cannot point to the root, it 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 cannot point to the root. So this will point to the new internal node created, and it will point to S. Okay. So we followed rule 2 and we modified the previous suffix link as well. Now the active node again is not root, it's Q right now. So follow the suffix link. So by following the suffix link, we go to the root. So the active node will change to root, and we check the next character on the path, on the current path. So the current path, the current active point is one step in the direction of F from the root. So this is the current point right now, and the next point is again not the current character. So we'll have to create a new path and just assign it the $sign. And as per usual business, the new character will get its own suffix link which will point to the root, and the previous suffix link will need to be modified. So we'll erase this uh, suffix link which is pointing to the root right now, as it will point to the new internal node. So this is just here, and this was F from the beginning, so this can be F again, and this was the root, and this was pointing to the root, and this was also pointing to the root. Let's just make it a bit tidier so that it is easier to follow. Alright, so what we did is we created a new node and we modified the previous suffix link. Now as the active node is root and the active length is not 0, we modify the active length and the active edge accordingly as per the rules. So the active edge becomes 3 and the active length becomes 0. Now as the active length is 0, of course every time in this pass, whenever we created a new leaf node, the remaining has to be decreased. So the remaining was decreased by 3 as we made 3 new leaf nodes, and as the remaining is 1 and the active length right now is 0, we'll have to ask if there exists a path from the root to the current character. It does not. So we have to create a new path starting from the root to the $sign. Now as rem is 0, as a new leaf node is created, as the rem becomes 0, as the new leaf node is created, we reach the end of the phase, and this was also the last phase, and thus this will be our new suffix tree. So does this cover all the suffixes? Let's check. So the first suffix will be DEF, DEG, DEF $sign. So this is the one which it covers. Then the next one is E, F, D, E, G, D, E, F $sign. So this is the branch for that. Then next one is F, D, E, G, D, E, F $sign. It is this one. The next one is D, E, G, D, E, F $sign, which is this one. Next one is E, G, D, E, F $sign, which is this one. Next one is G, D, E, F $sign, which is this one. The next one is D, E, F $sign, which is this one. The next one is E, F $sign, which is this one. The next one is F dollar sign, which is this one, and the final one is only the dollar sign, which is this one. Now we have to name all the leaves. So the final step is naming all the leaves. So the leaves will be named as follows, as we had discussed earlier. So the leaves are named by a DFS traversal, and the DFS traversal is applied as follows. So we'll start from the root. We'll start from the root and we'll follow each and every frame. So we'll start from the root and we'll go to each and every leaf. So let's start from the root and we'll go for this leaf. So the length of the string is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And the number of characters you encounter is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 minus 10, this will be 0. So this is 0. Then we'll go here. So 1, 2, 3, 4. So this will be 10 minus 4, which is 6. Then we'll have 1, 2, 3, 4, 5, 6, 7. So this will be 3. Next one is here. So 1, 2, 3, 4, 5, 6. So this is 4. Then the next one is 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 1. Similarly, this one is 7. This one is 2, 3, 4, 5, 6, 7, 8. So this is 2. This is 8. This is 8. And this is 1, 2, 3, 4, 5. So this is 5. And this is number 9. So as we can see, each and every suffix is created, represented, and each and every leaf has been named. So this is how we create suffix tree using Ukkonen's algorithm with all the modifications and the new concepts which we had defined earlier. Of course, in practice for a human it takes a lot of time, but as we will see, this is more efficient for a machine as compared to the previous method using only the 3 rules without any modifications and active entities or suffix links, which took a cubic amount of time. So let's see that what is the time complexity of this particular algorithm and get to know that how it is more efficient.
So I hope everything was clear from the example. So this is how Ukkonen's algorithm can be applied to design a suffix tree. But this still hasn't answered our question. The question was that can we solve the longest common substring problem in linear time, and we concluded that we will be able to solve the problem in linear time provided we can compute the longest common substrings requirement, that is the suffix tree, in linear time. So if you observe carefully, Ukkonen's algorithm reads every character of the string twice. So therefore there are 2n operations involved for a string with length n. Therefore the algorithm is of order O of n, and thus we can firmly say that Ukkonen's algorithm constructs the suffix tree in linear time. And we know that if a suffix tree can be constructed in linear time, longest common substring can also be calculated in linear time. Therefore this implies that the longest common substring problem can be solved in O of n time. Thank you.